Yeah, I'm not going to go further back because I'm kind of scared of that animation now. I'm sure it's got nothing to do with it, but why is this something? Okay, where was I? There's incredible diversity of exoplanets. You can go from things like hot Jupiters to wide orbit giants to ocean worlds to rocky planets like Earth to lava worlds. And you can see that for a lot of these things, I did go back. Okay, we're going to try it. They're detected by the transit method. This is great because this actually allows us to. It didn't do it. It's not good. And so for transiting planets, this is good. We can actually learn things about their atmosphere. So with transit spectroscopy, we can probe things like the chemical composition, and we can constrain vertical and horizontal temperature and pressure profiles. We can look at things like aerosol properties. We can maybe perhaps detect things like outgassing on the surface, probe if these planets potentially have oceans, and we can use this information to understand things about the physical processes that govern how a planet evolves and what's going on inside their atmospheres. And we can take, populations of these planets that we learn things about, and we can look at population trends, and this allows us to start to answer big questions like, what is our place in the universe? Is the planets in our solar system similar to the galactic population of exoplanets? Is Earth special in any way, right? Is it representative of the planets that we see in the galaxy? And yeah, this question of how unique our own solar system is the trends in the solar system like mass metallicity that are borne out in the galactic population too. There is another question that you can ask, also a big one, which is, are we alone? Right. So the way that people try and answer this question with exoplanet spectroscopy is practically very different from the other questions. So one of the main ways, it's not the only way you can do it. So this does not rely on inferring bulk properties of a large number of exoplanets. Typically, what people do is they look for something called a biosignature. So I'm not going to talk about what a biosignature is or how robust that school of thought is looking for one molecule, but let's say that there is such thing as a biosignature. And they're looking for the presence of a single gas in an exoplanet. And that should answer the question. If you believe in biosignatures and their robustness, that should answer this question. And the problem with this is that everything kind of precariously hinges on robustly identifying a single molecule or a set of plausible molecules in one atmosphere, one exoplanet. And that's precarious. It turns out that if in the regime of the data that we have, whether you detect something depends on how you define detection, right? And the kind of choices that you have to make as a scientist actually end up affecting whether or not you make a robust or high signal to noise detection of a potential biosignature. So I think what I'm trying to say is it's precarious, this endeavor. So, quick basics of it. Kind of a little bit zoomed in. I don't know what did it. Yeah. I think we can deal with this though. Yeah, good. So we have an exoplanet that goes in front of its host star, and it blocks some of the light of that host star. And now some of the light from this host star is going through the atmosphere of the exoplanet, and different absorbers block different amounts of light at different wavelengths. So if we take this light curve, we measure the transit depth. We measure the transit depth, which is basically the size of the planet in different wavelengths. We can back out something that looks like a spectrum. So here it is. Let me try and say, well, how do we fix it? Cycle it. I should remember this.
I think what happens is that there's a part of the software that detects motion.
Oh, maybe I can't move. Maybe that's it.
No, I think anyway, it feels, yeah, just. I will cycle through immediately.
I'm going to stop moving.
It's not you, I think it's the animation that does motion.
Oh, I see. Okay. Yes. That'll be
zooming on the whatever is moving.
Oh man, it's going to have some trouble with slides to come. Okay. So what do our observations look like, right? So this is the wavelength, or you can think of this like a color, and this is the planet size, or that transit depth. And so you can see here we've got observations, and this is some spectral imprint of some gas in the atmosphere of the planet. So the natural questions we want to ask is, what is this? And how much of it is there, right? So this is where we build models, right? So these are the cross sections. So these are the kind of spectral fingerprints of the molecules. So wiggles here will show up as wiggles in your atmosphere. And the thing here we want you to note is that it's kind of busy, right? All the things that we might want to detect in an exoplanet atmosphere, their signatures are all overlapping together. Okay, so you kind of have to build a model where you jointly fit a bunch of these things together, trade off the degeneracies, and see what you might robustly detect. So yeah, I mean, it's basically just matching patterns, right? So, you can think of the model building exercise of like, what gas fits what wiggle in the spectrum, right? So if you look at the spectrum of CH4, you look what its spectral signature look like. Looks like that. It's probably not CH4, right? Probably not H2O. CO2, right? This is a very easy example, right? So this is incredibly high signal to noise detection of CO2. We know what the cross section looks like, and it's got this incredibly high abundance that's this sharp feature in the spectrum. So it's great. We can use this to build models and back out the chemical composition of an atmosphere. So it's just worth mentioning the kind of revolution of the data that we've collected. So this is a HST spectrum from more than 10 years ago. You can see here, this is what our data look like. It's okay. There's something there, right? There's something there. And you compare that to the James Webb data of today, right? We've seen a massive change. We're getting broad wavelength coverage across the James Webb instruments. We're getting incredibly high resolution spectroscopy with incredibly precise measurements. And this is great. But it's really put the modelers on the back foot. So we're in a regime. So with HST, we're kind of scared to increase our model complexity and overinterpret the very sparse data. But with James Webb, we're actually seeing signals, wiggles, features in these spectrums that we can't actually explain with the models that we have. And that's good. That puts us in the discovery mode, right? But you also have to be careful. Okay, there's a risk here, is that we're adding stuff to our models that are not kind of sure to explain these new bumps and wiggles that we couldn't explain before. So this is great for discovery. You have to be cautious. So how do you model exoplanet? There are two strategies actually. So I'll talk about the one on the left. So this is a spherical cow, and so these are free models. So what you do here is you pick a selection of gases that you might think are in your atmosphere, like H2O, CO2. You then fit for the abundance of each of these gases. And you let the data drive. You say, okay, data, you give them a set of gases, and then you say, okay, how abundant are each of these things? And you let this kind of mold to the data. So this is good, but you really are in the data drive, right? So there's no guarantee that there's much physics in your interpretation. So you've got to be careful with these kind of models. You can end up in a scenario where, given the temperature pressures in the planet, you come up with some unrealistic mixture of gases that really wouldn't survive. The other side of this is you can do, your full physics model, which has all sorts of physics in it, and you don't fit for the abundance of gases. That's something that's worked out in your model. You fit for kind of bulk properties of the planet. So you specify the metallicity, the temperature profile that it's in, and then the abundances end up being fixed. So the good thing about these models is there's a lot of physics. And so your model's going to be physically accurate to how much physics you've got in there, right? But if you've not included some things, so, for example, there's a lot of equilibrium chemistry models, but not so many disequilibrium chemistry. So if there's something in your data that you haven't included in your physics, these models are kind of rigid. They're not going to let you kind of discover that extra physics off the bat. So people do both. And you can usually do both and check that they're consistent. That's a general strategy. The one thing I will note is this side is a lot more computationally expensive. Your inferences might run in your one forward model, so go from parameters to realization of the data might take a second. This might take 10 hours. So there's a huge difference in the computational cost of these two things, but they're both valuable. So I'm going to talk about detection, what it means to detect something in the atmosphere. So these are the kind of things I like to think about. I want to get you to think about what it means to detect something robustly. So the first thing you might want to ask is the signal robust? Is the wiggle that you're seeing really there? How high a signal to noise is it? And do we expect there to be a signal or a bump there on your spectrum? Right. A lot of this is tied in with like how you do your instrument systematics. Some of the James Webb planets, like the rocky planets, we're seeing kind of flat spectrums. So are you over-interpreting noise? Perhaps. But I think if you've got a good reason to believe that there's an atmosphere there, my view is that you should go ahead and fit it, even if the signal to noise is very low. The other important thing to think about is signal attribution. So say you detected CO2 like we saw in that previous spectra. You want to ask yourself, do I know where that detection is coming from? Is there a clear CO2 feature that I can unambiguously attribute to CO2? And robustly, so if I add another gas into my model, does my understanding about the physics of what's going on, the abundances change? Or is the adding CO2 in my model kind of robust to the things that I might plausibly add? And the second thing is interpretation, right? So given that you think you've detected something, you should think about the physics of what's going on. Is this plausible? What does that mean to, can you make a sensible, testable prediction given that you've detected H2O or whatever in your atmosphere? Does it make sense physically, right? You've got to think of things in the broader context, right? Fitting models to data for one object can only get you so far. So how do we actually detect, so how does the field detect something currently? So this is actually basically Benecke and Sager in 2013 suggested a way how to do this, and the field adopted this, and it's not changed since. And so what you do is you look at a competition between two different models. You build what's called a reference model that is maximal. So this model contains all the different chemical species that you plausibly think are in the atmosphere. You then assign a score to this model. I'll talk about the score that people use, which is the Bayesian evidence in the next slide. But you say, okay, how good is this model at explaining my data? Then what you do is you remove the species from the model that you're interested in detecting. Okay. And then you score the model without these species again, right? And then you say, if the reference model outperforms the model without the species by some threshold amount, you say that's a detection. Threshold amount is the field picks 2 sigma. It's not clear what that sigma means. It means something. And then you basically repeat this for all the species you want to detect. Okay, so that's how you do a detection in exoplanet atmospheres. And this scoring method is you use this Bayesian evidence. So that's on purpose up there. People think that this is the way to do model comparison. It's just a way. It appears in Bayes' formula, which we'll go through in a minute, which makes it a natural choice. Bayesians like it, but it's just a way. It's not the way. It'll tell you something about your problem. It's not going to tell you everything about your problem. So this is Bayes' formula. So this is your posterior distribution, your probability of model parameters given the data. So this is like the constraints that you might derive, like how much CO2 is in the atmosphere. This would be an example of a posterior quantity. This is your likelihood. I think Bayes' theorem is kind of rough to physics, right? So all the physics that you want to code up, your models, everything is in that tiny conditional bar there. That's the entire physics is right there. That's the looking that it gets. And then this is your prior. So this is the prior that you expect over the model parameters before you see data. So what is your expectation on the abundance of these molecules before you see the exoplanet spectrum? And then this down here is the Bayesian evidence, or the probability of the data given the model. So this is the thing that's used. And reading the literature, I was trying to, why do people use this? And the conclusion that I've come to is because somebody built an algorithm that can calculate it. This thing is kind of hard to calculate it. It's kind of hard. It's expensive to calculate. But people in around 2008 came up with an algorithm called nested sampling, which gets you your posterior distribution, which is what we're interested in. But it also gives you this quantity for free. And so I actually think that the reason people use it is because they could compute it. And it's nice. It's Bayesian. It all kind of fits together. And so it supposedly penalizes model complexity. So what this means is that if you say you have 2 models, one of them is slightly more complex than the other, but they explain the data just as well, this criteria is going to prioritize the simpler model. This applies some kind of Occam's razor to your analysis, but it's not clear what that means. How strictly a model is being penalized. You say if you increase the number of parameters by a couple, what penalization does that correspond to? Not clear. It's actually dependent on minute mathematical details of your problem that you don't care about. So this is good. This is good. It seems like it's good. It depends on and can be sensitive to your prior. We can go about, why that is if people are interested. But it basically means that you've got to be careful if you are not sure about your priors beforehand. You want to check if increasing the prior changes your Bayesian evidence by a lot. In most cases it doesn't, but in some cases it can. And the important thing here is if you're, considering a set of models to explain your data, if you don't have the correct model in that set, doing model competition and scoring models by the Bayesian evidence is not going to get you the right answer. You've got to have a complete or near complete set of plausible models. You've got to be sure that you're probing the whole model space. If there's models that are plausible that you're not checking, there's no guarantee that the Bayesian evidence is going to give you anything useful. Okay, so this is my view. So all of this relies on pairwise model comparisons to detect something. I think this is a completely losing strategy from off the bat, right? So if you have like 10 molecules in your atmosphere, this is how many pairwise comparisons you'd have to do to search the space. Completely impossible, right? People build this reference model with all the molecules together. That's a choice. Is it the choice? I don't know. Right? It's a choice, right? And so if you really want to exhaustively search this space, we're in this regime now with James Webb. We're fitting 20 things to the data. There's no way you can search that space properly. Off limits. And then, you get yourself into weird scenarios, right? You can imagine if you have like one large model that's got lots of parameters and you remove one gas and this difference, so this is the better model fit on this axis, your detection significance is going to be the difference or these two things, so it's kind of small. Whereas if you pick a slightly smaller model that doesn't really explain your data better, and it's just, maybe slightly better, negligibly better than your large model, and then you take one gas and everything falls apart, this scenario is actually going to give you a bigger detection significance than this scenario. Is that what you want? I don't know, maybe not. But everything's relative. So you can end up in a weird part of the model space where you just so happen to compare a reasonable model to a completely terrible one. And then you've detected a gas. Okay. So this is okay. You just have to be aware of it. So back to K218b, what I'm not going to talk about is this detection as biosignatures. This is debated. Are they actually biosignatures? Who knows? There's, you can create them without having to invoke life. And whether or not detection of a single biosignature is a good way to search for life. And we're going to talk about that.
Let's turn it off. Spam.
What I am going to talk about is the statistics. So I've kind of primed you all to get here that got us into this detection and some general alternatives we can actually do instead of doing this going forwards. Okay, this is going to be an animation slide. Sure. But, oh, no, it's not. Yeah, no, it's not. Yeah, so this is the data for the Madison et al. 2025 paper. So look at this spectrum. It's not like super clear what's in there, right? There's no high signal to noise bump anywhere, right? And you can see where they've attributed these two biosignatures, DMS and DMDS, here and here. I mean, there's some wiggles here, right? But it's not clear, right? And if you look at the cross-sections of things that are in this space, so this is the DMS and DMDS cross-sections, right? There's a bunch of things down here, some hydrocarbons that could also explain what's going on. There's bumps and wiggles everywhere. It's all degenerate. Okay. So they claimed a significant detection of both of these things together. How did they do that? Okay, this is okay. So this is the normal thing to do. You construct your maximal reference model, about 20 molecules. You then remove the things that you're interested in. So they're interested in both of these things. And then you look at the difference. So this is so if a model's higher up here, this is a better fit to the data as according to the Bayesian evidence. And this is a sigma detection translated into some sigma scale that they came up with. So this is saying that if you do the normal thing that everybody has done before with these two gases, you have a 1 sigma detection and you go home and you don't write the paper. Okay, so now I'm going to try and walk you through what they did because it's not clear from the paper what they did, but this is what they did. They didn't take their maximum model as reference. They built a new model that just contains CH4, CO2, DMS, and DMDS. This was preferred by 1.3 sigma in the Bayes factor over the maximal model. So again, this is basically the same as the maximal model. This is an insignificant increase in the evidence. Are we with me? Okay, it's going to get more complicated. Mm-hmm. Then what they did is they're like, okay, let's just remove DMS. No change in the evidence. Okay, so, this should say it's not there, right? Okay, but they didn't stop.
Yeah.
So then they're like, okay, if not DMS, let's try and remove DMDS. Okay, this gives something, right? Slight change. And I'm like, no, let's remove both of them. All the way down to now you're just left with CH4 and CO2. And this is where the 3.8 sigma detection of those gases came from. Okay. I'm not saying what they did was wrong. I'm just saying that they made a choice very different from what's conventionally done. And they managed to squeeze out this, what's considered a significant detection of this gas in the atmosphere. But this is all a game of pairwise model comparison, and who knows if we're in the correct part of the space that's interesting, right? And yeah, they had to remove both gases at the same time. So they didn't detect. So the way that this is phrased in the paper, incredibly confusing, is you don't detect DMS or DMDS. You're detecting one of them, but you don't know which one. Okay. Did that make sense? Okay, good. Okay, yeah, so this is a choice. It's not clear that it's the wrong choice, but it's certainly a strong choice to try and drive a detection out of a spectrum. So we then had a look, and we thought, there's other plausible gases that can explain these wiggles. So with a huge amount of compute, we basically were like, okay, let's actually try and explore the model space, right? So we actually iteratively went through many hydrocarbons and played their game. So we did the same thing as them. We said, okay, let's build a reference model with just CH4 and CO2 and put this molecule in and then remove it and see if we can get a detection in exactly the same way. Yeah, we ended up detecting 59 molecules at high significance doing this. So whatever we put in, we were able to manufacture a detection. And a notable one, right? Because, you can claim to be like an expert model builder, some gases are more likely to be in the planet than others. So there is a sense of like, as a scientist, you do have some kind of choice about how you build a model, and you should do that carefully, and that's okay. But notably, we got a detection that beat the DMS detection of the C3H4, which is very plausible, expected in methane-rich environments. It's directly measured in Neptune and the solar system, and it's actually predicted to be in the atmosphere of K218b. So we found a plausible alternative that beat it by the road method, right? And so, we're not saying that we detected this in the atmosphere. So if you read the paper, we're not saying we detected anything. The point is the opposite. We can't really detect anything. You just get out what you put in if you do this way. And so the only thing you can conclude from this data set is you can't really robustly attribute any of the spectral features to DMS or DMDS. Neither can you uniquely attribute it to this, right? Basically, if you're going to play this game of this minimal model, you're going to basically get out what you put in. So there is really, you think about data, there's not a lot of information in here. And this is what we're getting at. So yeah, if you run one of these expensive physical models, you actually see that many of the things that we detected, if you run your physics, you put a lot of physics, equilibrium chemistry. This equilibrium chemistry, you find that a lot of these things that we detected are actually plausible constituents of the atmosphere. So this kind of makes sense in terms of physics as well. But not that we were claiming that we detected anything, but just to show that there's plausible things that you can put there instead if you wanted to squeeze out a detection from the data. So what did we learn? So, when we wrote this paper, I think some of the lessons that came clear is that you don't want to hinge any conclusions, especially if they're extraordinary, on single pairwise model comparisons, especially when the space of models that you've got is vast, right? There are some problems where you roughly know all the models, right? That's okay. You can do some pairwise comparisons. But in a case where you don't know what you're looking at and there's many ways to build your model, you really don't want to do this because you're probably not going to likely be anywhere near the right answer. And this thing of relying on a single metric to assess models, right? All they did was compute some thing that they could about their model, the Bayesian evidence, see that it changed by some threshold amount, and they called it a day. They said, we've detected, right? It's telling you something about your problem, but not everything. You've got some information. If this model has a higher Bayesian evidence than another, that tells you something, but it doesn't tell you everything. There's a lot of other things that you can learn. And yeah, I think it's a lesson on don't. You don't have to base your conclusions on a winning model. You don't have to say, this is the best model. This is where I'm going to draw our conclusions. You can do more flexible things. You don't have to be so set on finding your best model to do your science. And so I'll just talk about three things that we've developed in this collaboration that we've tried on different exoplanets. And so the first thing is interrogating your models. So this thing called cross-validation I'll talk about. It's very useful. It basically checks that if a model fit is performing how you expect it in the regions where you expect it to perform well. So like if you have two models, one of them thinks there's a feature at 1 micron, it ought to explain data better at 1 micron than a model that can't. You can check things like this. You cross-check, you can interrogate, you can figure out what's going on with your model. You can also take an approach where if you think there's some unknown feature in your data, you don't have to stick a biosignature in there to explain it. There's methods you can use to agnostically figure out that there's a residual and then treat it, with the caution that it deserves. And again, this no single winning models. You can do things like average over your models. If you have a bunch of models that give plausible explanations and you can't distinguish them from each other, you can just say, what's the average of my conclusions over those models? This is going to increase your variance on what you can say, give you lesser constraints, but it's going to be a more honest representation of the situation and the uncertainties involved. So the first one is cross-validation. So you can do something called leave one out cross-validation. So basically what you can do is you can train your model on your data set with one data point removed, and then you can try and predict that data point with your trained model. You can repeat this for all data points in your data set. And what this allows you to do is gives you a couple of nice things. You can total this score. So you're scoring each data point now, given your model. You can total this model score over the whole data set, and it gives you a performance metric. Like the Bayesian evidence tells you something very different about your problem. This is not sensitive to the prior. There's less constraints. It's less sensitive to not having the correct model in your set. There's some nice properties of it. And it also allows you to interrogate two competing models on the data point level, right? So I'll try and explain this. There's a lot of information here. So this is just simulated data with a model with H2O. This is all of these wiggly lines here in the purple. And then this is data that we generated. And then we tried to fit this with a model that was correct, the H2O model. And then this green model here that didn't contain a H2O, so this is not correct. You can do cross-validation on both of these models, take the difference at each data point, and then color the data point by the difference. So the red data points are where the H2O model explains the data a lot better than the green no H2O model. And the blue / white, the white data points are where it doesn't make a difference. And the blue data points are where the no H2O model outperforms. So you can see where the data significantly deviates. The H2O model is doing its job. So this is an extreme example to get you to understand what's happening here. And so you're learning something about, how your models are outperforming each other and whether that makes sense physically. So we actually took this and looked at an exoplanet. This was HST data a while ago now. And so we looked at the planet HAPI 41b. And the notable thing about this planet, it has this beautiful spectra at the time, all the way from HST, the near infrared, all the way to the UV, sorry, Spitzer to the UV. And they detected H- in the atmosphere. Low significance, but they detected it. And this was interesting because they presented a puzzle to the field. If you do those cross checks, you expect where the temperatures you expect H- to be, it doesn't add up with the temperatures that they constrain from the planet. So something's going on here, right? So you see here, right, the conventional wisdom, that the paper described is that they thought they were getting, so this is the H- cross section. So they thought they were getting all the constraints from H- in here, where you see this cross section goes down. Okay, so it's like, yeah, it's the WFC3 data that's constraining everything, and it's giving us this H- detection, but we're not sure why the physics doesn't line up. So we just did some cross-validation on this, and we found out that this data point basically is entirely driving the H- inference. If you remove this data point from your analysis, the detection goes away completely. So this is notable because it's not where you expect it, right? But it is in a region where there's something going on with the cross-section. But the notable thing is a Spitzer data point. People were convinced that Spitzer was reliable. And so, this is kind of a smoking gun, right? Your entire detection is not dependent on, some even distribution of data points where there's information. It's all the way down here in one data point, right? Which is something you don't understand if you don't do this fine-grained interrogation. And it actually helps you, right? It helps you see that maybe, you might want to take a closer look at your Spitzer reduction and see if, changing some of those knobs that you can turn on the reduction changes this data point, because it's likely going to have a large effect on your conclusions. Okay, good. So the other thing is this non-parametric methods for unknowns. So this is work done by Yoav Rotman, a PhD student at ASU. So instead of trying to put physics into your models when you have a bump that you can't explain, you can just use something like a Gaussian process to fit for it jointly. This works really well, so it devised this scheme where you can fit for like, correlated noise in your data that might come from something weird in the reduction, but you can also fit for unknown absorbers that are a correlated blob somewhere in your spectrum. It's really cool. So what we did is we did some simulations. This is just a simulated spectra. We put an unknown absorber in there, and then we tried to, so this is the truth of the water abundance. So if you have this unknown absorber in there and you don't model it, you just fit for your water and you just let this unknown absorber sit there, it biases your inference on the abundance of water in the planet. Whereas if you put a Gaussian process in there to kind of absorb and find this unknown absorber and then absorb it, you can completely debias your inferences. You've not made any, you've not made any claim that there's something there. You've not had to think carefully about how to describe this bump. You're able to get a reliable conclusion about the planet without having to invoke anything. You've just put some flexible agnostic thing in there to absorb what's going on, which is very useful. Yeah, and the final thing is model averaging. So here's an example of a spectrum with different models. These are all the medians of the different models. You can see that these models always kind of agree where there's data, but they don't agree where there's not data, right? And so these models, if you compare them with each other, they're kind of like, none of them are preferred by the data. So what do you do in this scenario, right? How do you, present constraints, parameters? You might be tempted to just pick one of them, right? Pick your marginally best competing model. And that might give you the blue posterior, but if you pick the other one that's just as good, you get the green posterior, right? You don't have to do that. You can just average over all of them in a very consistent, statistically rigorous way and get out a constraint that represents that you don't know what the model is. A lot bigger variance, but it's a lot more honest. It's a lot more, you're representing the true uncertainty in the problem, which is that you don't know your right model, and you're not depending your conclusions on knowing it. You're saying, I don't know which one it is. All the conclusions and all of the things that I derive from this are just propagated naturally. Okay, talked enough. There's my summary. Thanks for listening.
We have time for a few questions.
I have a lot of questions, but
Good.
that was wonderful. Thank you so much. Let's see, because you talked about model averaging at the end, I'll kind of merge two of my questions together, which is, what's wrong with just looking at what you've inferred from the full reference model? Because that's got all of the complexity in it. Why bother with the selection process? And then maybe that touches on the model averaging, and that I'm kind of curious, does the result from the model averaging look like what you get if you just retrieve with the most complicated model?
Yeah, no, it's not always clear. So the first question, it depends on your problem. When you put something in your model, that's a strong assumption. Even though if you run your analysis and you don't get strong constraints, that can have a knock-on effect to all of your other constraints that you're able to derive from the other parameters. This really is a strong operation to put something in a model. And so the reason why you might want to not use the full reference model is if you are claiming, a conclusion based on your reference model, a caveat in that conclusion is that your conclusion relies on all of the gases actually being present. And that might not be true. And so putting something in your model can be strong, and you have to caveat all of your downstream conclusions that thing is actually in the atmosphere of the planet. If that makes sense.
A little bit.
Okay. And the model averaging, what was the question?
I was curious about, for the model averaging, what on the right-hand side, the constraints that you get, how does that compare to if you just ran the most complicated permutation of all of those that are on the left-hand side?
Yeah, it probably has less variance because you've made where this extra spread is coming from is the fact that you're kind of building in the uncertainty that you don't know the model. So that will always create more variance in your answer. So you're probably going to get something that maybe looks similar, but it's going to probably have a tighter variance. It's going to probably be more overconfident, I would say, generally.
Thank you for a great talk. You mentioned a little bit how you considered 90 other molecules.
Mhm.
Most of those aren't going to be based on line parameters, but probably from cross sections.
Yes.
So what degree does using cross sections versus line parameters influence these results?
Yeah, I don't know. I mean, we're using what's available. Yeah, there is certainly, I don't think any work's been done in actually, propagating uncertainty in the cross sections to the analysis. I think that's a really good idea to do. So I think my understanding is that some cross sections are known a lot better than others, and people treat them all the same. And so you might want to fold that uncertainty if you have a terrible cross section that's highly uncertain. It'll have some variance across it. Yeah, you could certainly devise a scheme where that uncertainty is included in your inference, and I don't think people have done it. With the Gaussian processes as well, we're running experiments with the ARC. We can actually, if there's a strong signal in the data, we can actually learn the shape of an unknown cross-section of James Webb, which I think is interesting.
A good one.
Oh, for this propane, what makes it a Neptune?
So again,
what makes propane in Neptune's atmosphere? Is it something we see, like, is it temperature dependent? Do you only get it in cold atmospheres? Do you see it in like organic plumes of pollutants here on Earth?
yeah, I'm not sure. Yeah, there probably is some plausible physical mechanism that creates it easily. I don't know if Daniel might know it. No. Yeah, I'm sure. I'm sure there's some plausible mechanism that'll do it.
You mentioned H minus, which is a major source of opacity in atmospheres such as the stars of the sun, such as the sun. I missed what you commented about H minus, because to get it, you need a lot of sodium and potassium elements with low ionization potentials and have to be in the vapor phase.
Yep. Yeah. So there's this paper that claimed that they detected it, and so I think they did have quite strong detection of sodium as well. But it didn't make sense in terms of the equilibrium retrieve temperature of the planet.
Temperature's too low.
Right.
That's right.
Indeed. So we thought that they probably didn't detect it, so we did this model interrogation and found out that it all relies on a single unreliable data point. So there's probably a problem with the data instead of an actual genuine detection of this gas. So yeah, you're right.
I wanted to check if anyone online has a question. And go to online questions. So feel free to unmute and. Okay, I think that is a no. So back there. Sukrit.
I think someone else has
Okay.
a question.
Hi, thanks for the very interesting talk. So I have two questions. One, is related to the leave one out validation that you were mentioning. I was wondering if that can be generalized, where at each wavelength you sample the data according to the error at that wavelength, and then fit your models to resampled versions of the data?
Yes, sir. I think that is automatically included in this scheme. So this quantity is an expectation of your posterior put through the likelihood, which captures all of those uncertainties. So I think this already naturally takes all of that into account. So this will take your posterior uncertainty into account in your model, and also takes into account the fact that the data has an error bar, so it can be plausibly within that. That's all taken care of in this scheme.
And my second question, so I'm not an expert on exoplanets, so this might be naive, but so when you mentioned that you established the significance of a model by removing one species, right, and then reevaluating the fit. Mm-hmm. So when you remove one species, do you need to worry about are you changing the physics of your model, and do you need to alter the compositions of other species, given that you have removed one species?
Yeah, for sure. So the free models, which is this is what people do the game in of removing gases. Absolutely. So the free model might compensate by increasing the abundance of a different gas to compensate for the fact that you've removed one, right? But what it's not going to do is compensate and care about the implicated physics of that situation. So you could end up removing a gas and then causing an unphysical combination of gases in your atmosphere. That can completely happen with the free model, which is why it's important to check these results against some physical model, or even fit a physical model if you have enough compute. What people usually do is meet somewhere in the middle. They take the physical model, do the free model, and they see whether things agree. That's usually what's done at the moment. But yeah, if I had all the compute, I would just fit the physical model, but it's very expensive.
This is perhaps a little bit of a saucy question.
Good.
So you've basically identified ways to be much more rigorous in interrogating your data. Have you applied these techniques to some classic discoveries in astronomy and planetary science and seeing if they hold up? Like, I guess what I'm trying to ask is exoplanets or being a little bit less rigorous, or has our standards of rigor improved in an absolute sense? Or
No, I think with exoplanets we're just in a tough spot, right? We have this incredible data. We have an incredibly degenerate model space that we can build with lots of different pieces. I think people here are not being less rigorous. I think the problem's just really hard. You really have to think carefully about how you construct the model. There's so many different ways to construct your model, and they're not always going to respect physics. It's not always clear that when you fit it, what's happening. So I think my answer to that is I haven't looked at like historic exoplanet stuff to see if this stuff overturns things, but
like before that pre-90 stuff.
Yeah, I don't know. Probably right. There's probably a bunch of statistics, but I mean, if you look at astronomy in general, science is actually incredibly, surprisingly robust to bad statistics, right? I mean, people do a lot of different things, not always correct, and discoveries are still robust, right? You can still put no matter how good you are at statistics, and careful if you don't base your conclusions on a single failure point and go with multiple lines of evidence to conclude something, regardless of how well you do statistics, you're probably going to make a good argument that's right. So science and discovery is actually pretty robust to this stuff. It's just when you want to claim something that's very important that hinges on one thing that you have to choose, that's where you have to be careful. So biosignature and exoplanet, be careful.
So I would just argue that as you go to cooler and cooler planets, right? And then also if you potentially consider an ecosystem that could be there, then basically the complexity of the parameters is really
Yes. Yep.
I think that Caitlin has a question.
I just want to follow up on Sucrit's point there. I mean, but you sound very optimistic in that discussion, but I would say otherwise the pessimism seems like a more fair assessment of what's been happening. I mean, what about taking some brown dwarf atmosphere data where we have older models at lower resolution, where can you validate whether or not you would recover the correct inference for composition that you get with a much higher resolution JWST spectrum, for example?
Yeah, you could do stuff like that. And yeah, I don't know. Yeah, absolutely.
I understand right now you're right. You're basically saying, be careful, you could be wrong, but you don't want to call out everybody for being wrong. And I get that there's some reason that you don't want to, but I think it would be very useful to the community to show some explicit cases of you could have inferred, this is actually wrong.
For sure, yeah, for sure. And we did that with stuff like this, right? We took these alternative ways of thinking about how you detect something and applied them to test cases in the literature. But being somewhat critical of the way that people are doing things, I feel like I have to have some kind of solution, right? And I think I was thinking kind of about this. We talked about this, and I think we need to go back to the basics. So, for example, for K218b, a good question is, what would I believe, right, was a detection? And I think I would believe something that went along the lines of this. If they made a detection in the MIRI band of DMS, they said, this is the detection. And if they somehow made a testable prediction about future data, said, this is going to happen in this wavelength band over here with nearest or whatever, right? And then they published their paper, then they went out, collected that data and showed that the DMS model predicted the correct thing, that would be convincing. But we're often the case now where we collect panchromatic spectra of everything. We're kind of inferring everything together. And I think we've lost this case of you have a theory can be as small as I think DMS is in the atmosphere of K218b. That theory should have some testable prediction about future data that you've not collected yet. I think that would be convincing to me. And I don't think we do that anymore. Because you do it for big things, right? It's great, you do it for big projects. But for the small things where your science depends on detecting one thing, for example, you can do the same thing. You should make something that's testable, publish your results, and then go and test it.
Okay, excellent. Let's thank Peter for the